All right, hello. So we are going to switch topics again. We're going to come back to the solar system and talk about the closest star to Earth, which is, of course, the sun. So right off the bat, I want to give big props to the woman who is integral to our understanding of the sun and other stars, and that is this woman on the screen here, Cecilia Payne-Gaposchkin. She was a British-born astronomer and, frankly, a genius. She started studying quantum mechanics at Cambridge, but Cambridge didn't allow women to graduate. So, at the encouragement of Arthur Eddington, who was a very big deal physicist, she moved to the United States where she worked and studied at Harvard. So she realized while she was there, through her study of stellar spectra and her knowledge of quantum mechanics, that the sun is mostly made of hydrogen and helium. And this went against what most astronomers thought at the time. They thought the sun was probably made of silicates, right, of rock, of the same stuff that Earth is made of. She was actually dissuaded from publishing her results by the very man who, a few years later, published a paper basically admitting that she was right. So, Cecilia Payne's dissertation, where she first asserted that stars are made of hydrogen and helium, is now widely considered one of the best astronomy dissertations ever written. And she went on to become the first woman to be a full professor at Harvard and the first woman at Harvard to be chair of a department. So, again, she was a genius, and we owe a lot of our understanding to the sun and stars to this woman. But back to the sun itself. So, as Cecilia Payne realized, the sun is a big ball of mostly hydrogen and some helium. It takes 100 Earths to span the sun's diameter, and the sun is 330,000 times the mass of the Earth, weighing in at almost 2 nonillion kilograms. So that is a 2 with 30 zeros. It plays host, as we know, to 8 planets and an untold number of dwarf planets, asteroids, and comets. The sun is in some ways an extremely boring star, and that is a good thing, right? It makes it possible for life as we know it. The sun is the source of the vast majority of energy that makes life go on this planet. There's no sun, no life. It emits almost 400 septillion watts of energy. That's 400 septillion joules radiated by the sun per second. That's four followed by 26 zeros. So that is a huge amount of energy. And the sun is a star, right? So it's pretty big and it's pretty hot. So maybe that huge amount of energy shouldn't be surprising. The surface temperature of the sun is about 5,800 Kelvin, or 5,500 degrees Celsius, or 9,900 degrees Fahrenheit. But the mechanism by which the sun stays so hot was unknown for a long time, and there were a few different hypotheses that were kicked around. One mechanism astronomers explored was something called Kelvin-Helmholtz contraction or gravitational contraction. So a Kelvin-Helmholtz contraction is a process by which the star's gravity creates pressure and heat in its interior. So as a star kind of cools down, the internal pressure holding the star up will decrease, and gravity will start to compress the star, and the star will shrink down. The compression will cause the interior to heat up again, which the theory went would make the sun hot. So it seems simple enough. The problem is that if you calculate how long it would take the sun to radiate away all of its energy at its current brightness, we have a star that will only last about 25 to 30 million years. And so we know from, geology, dinosaurs existed, 65 million years ago. Um, so we're pretty sure the sun has to be around longer than 25 to 30 million years. Um, by the time astrophysicists worked this out, there's obviously pretty good evidence the Earth was several billion years old. So the Kelvin-Helmholtz contraction simply doesn't give our solar system enough time to evolve to its current state. We need billions of years for that, not millions of years. But never fear, we have other options. So another option that was kicked around is called chemical burning. So astronomers, myself included, will often say things like a star burns through its fuel or something like that. But we don't mean burning. Burning is an exothermic reaction, meaning it produces heat. Um, and it needs, it's a chemical reaction between fuel and oxygen. Um, when you light a match, right, that is burning. It's a chemical reaction between oxygen in the air and the fuel on the match head. So astrophysicists explored this idea that the sun may be so hot because it's literally on fire. This is somehow worse, though, than the Kelvin-Helmholtz contraction. The sun simply doesn't have enough stuff to sustain the type of burning that is needed to produce its brightness for very long. It can be sustained for maybe 10,000 years. And for those of you keeping track, that's much less than 25 to 30 million years that we got out of the Kelvin-Helmholtz contraction. Um, and even that, isn't enough for the evolution of the solar system, right? So Kelvin-Helmholtz contraction is out, so is chemical burning. It just doesn't produce enough time. But what else can release energy? Like, what else could this possibly be? So we have one more play, right? Thanks to Albert Einstein and his special theory of relativity. According to this theory, mass and energy are essentially equivalent. Mass can be converted into energy by this famous equation on the screen, E equals mc squared, where E is energy, m is mass, and c is the speed of light in empty space. Cool. Okay. Yes. So what type of process will convert mass into energy? Well, a thermonuclear reaction, thermonuclear fusion. So what is thermonuclear fusion, right? It's fusing together of two light nuclei to form a heavier nuclei. And in that process, energy is released. So in this process, the mass of nucleus 1 plus the mass of nucleus 2 is actually more than the mass of the heavier nucleus 3. The missing mass is converted to energy according to E equals mc squared. So what is happening though is that there's a difference in what we call the binding energy, or the energy it takes to tear apart a nucleus of nucleus 1 and 2 and nucleus 3. Nucleus 3 needs less binding energy, and so some energy is simply radiated away. Nuclear fusion can result in the release of quite a lot of energy. It's been kind of the holy grail of sustainable, long-term, clean energy production. But it's extremely hard to get the right conditions for it on Earth. It needs a place of extremely high density and pressure, like the center of a star. So under these conditions, atoms are completely ionized, right? Or stripped of their electrons. You need high temperature and pressures to force all of these positively charged nuclei together. But this works. For the sun, at this stage of its life, hydrogen nuclei fuse together to make helium nuclei in a process that converts a small amount of mass into a large amount of energy. So over the lifetime of a star, there are a couple of different nuclear fusion processes, but the sun is currently going through one particular phase of its life where the dominant form of energy production through nuclear fusion is called the proton-proton chain, or the PP chain, or hydrogen burning. But remember, not chemical burning, but it's still nuclear fusion. I'm going to go over probably some more details of this than you really need to worry about too much, but I do think it's instructive. So the PP chain is called this because it starts out as the fusion of two hydrogen nuclei, which are just individual protons. The chain consists of three reactions that result in the conversion of six protons into a helium nucleus plus two additional protons. Okay, so step one in this chain is the fusion of two hydrogen nuclei to make the nucleus of something called deuterium. So deuterium is basically it's heavy hydrogen, basically hydrogen with an extra neutron. So how does this happen? So you start off with two protons, you should end up with two protons, right? Well, not necessarily. The two proton combination is actually not stable, which causes the nucleus to lose energy. That process causes one of the protons to actually turn into a neutron, which is a more stable configuration. This is generically called beta decay, and this type of beta decay is known as proton conversion. So that is step one. We get two hydrogen atoms combine to get a basically a heavy helium nucleus, deuterium, and also we get a positron here and a neutrino right here. So you have this collision of protons that turns into a deuterium nucleus, plus that positron and neutrino as a result of the beta decay. That deuterium then needs to collide and fuse with another proton, which results in helium-3 nucleus, so kind of a light helium nucleus, and a gamma ray, or a high energy photon. So that is step two right here. We have this deuterium collide with this normal proton. You get a gamma ray and a light helium nucleus. So steps one and two need to happen at least twice, because for our third step to happen, we need two helium-3 nuclei. So we just copy this up here, paste down here. It's the exact same reaction. So step three involves the fusion of two helium-3 nuclei into one helium-4 nuclei and two protons, which can kind of get right back into the mix again. So in the end, this process converts four hydrogen nuclei into one helium-4 nuclei, two high energy photons, and two positrons and neutrinos, which or the product of the beta decay. These two little gamma rays are the energy released by thermonuclear fusion. So how much energy do we actually get from this? So the mass lost in this reaction is about 4.8 times 10 to the negative 29th kilograms, right? Small, but this is the difference between the mass of four hydrogen nuclei and one helium nucleus. This is 0.7% of the mass of those four hydrogen nuclei. If we just plug that into E equals mc squared, we get something like 4.3 times 10 to the negative 12 joules of energy. So this may not sound like a lot, but for something the mass of the sun that is made up almost entirely of hydrogen, it can add up to a lot. In fact, a kilogram of hydrogen reacting in this way will produce 6.3 times 10 to the 14th joules of energy and produce the observed luminosity of the sun. Um, and to do all this, it would have to consume 600 billion kilograms of hydrogen every second. But remember just how massive the sun is. The sun is 2 nonillion kilograms. So at this rate, the sun has enough hydrogen to keep it shining for another 5 billion years. And given that we think the sun is about 4.5 billion years old, we have a solidly middle-aged star. For thermonuclear fusion to take place, it has to be pretty hot, right? Over 10 million Kelvin. The temperature on the surface of the sun, which we can tell it's a black body emitter, so we can tell the temperature, it's about 5,800 Kelvin. So this fusion has to happen inside. We can't actually see very far beneath the surface of the sun, though, so we have to kind of use what we can see and the laws of physics to figure out what the inside of the sun actually looks like. There's one thing we can definitely see. The sun is not undergoing any dramatic changes. So what I mean by that is the sun isn't expanding or collapsing, and it's not significantly cooling or heating up. So this means that the sun is in two different types of equilibrium. We have hydrostatic equilibrium and thermal equilibrium. And both of these are important for our model of the sun. So let's start with hydrostatic equilibrium. This is just a fancy way of saying that the internal pressure of an object exactly balances the force of gravity that wants to collapse the object inward. So the sun is a star, it has a lot of gravity, but the inside of the sun is very hot and heated gas expands. That hot gas creates an outward pressure that balances gravity, so the sun doesn't collapse in on itself. As you get deeper and deeper into the star, the pressure gets higher and higher, and more pressure means that the gas will heat up more and more. So there is actually a temperature gradient in the sun. But at any given depth, we can assume that the temperature is more or less constant, right? That it doesn't change with time. So this is called thermal equilibrium. We assume that the sun is in thermal equilibrium because it doesn't get hotter or colder with time. So for this to be, the energy generated in the interior of the star must be transported in some way to the surface where it can be radiated out into space. The sun will transport its energy in a couple of different ways, which divide the sun's interior into different zones. So the first zone is the core, right? The very center of the star. So this is where the energy is produced. It's very hot, about 15 million Kelvin. Um, it's about 14 times as dense as lead, with a pressure of about 10 billion atmospheres. So an atmosphere is the air pressure on Earth at sea level. So this is where the thermonuclear fusion takes place. It's about a 200,000 kilometer diameter or radius. I mean, that's about a quarter of the sun's radius. So it's a pretty substantial part of the sun. Outside of the core, it's too cool for fusion to take place, but the energy generated there must travel through it to be radiated away. So energy has to travel to the next zone, right? The radiative zone. This is the region of the sun where the energy transport process is called radiative diffusion, and that's what dominates. In and near the core, atoms are stripped of their electrons because it is so hot. So these electrons really can't capture photons. The result is that the slow migration of photons through the radiative zone. The migration is slow because this region is still really dense. So a photon is bouncing around like a pinball. It takes something like 170,000 years for the energy generated in the core to travel through the radiative zone, which is about 700,000 kilometers. So light, which we generally think of as very fast, moves at about 50 centimeters per year in this zone. Takes a long time. As we go further from the core of the sun, the temperature decreases. At some point, it gets cool enough for electrons and protons to come together again to form hydrogen atoms. Hydrogen atoms are really good at capturing energy, so they will absorb that light coming from the radiative zone and become more energetic. They become hotter. The hotter material will travel to the surface while the cooler material will sink in a process called convection, right? It's a lot like if you were to boil water on the stove. It's kind of that same process, except it's not water, it's actually just hydrogen. So we are now on to the convective zone. Energy can be transferred to the surface of the sun in this zone and radiated away. So you can see here we have, it's like an onion, right? We have this core here where nuclear fusion is taking place. We have the radiative zone um, where kind of radiation dominates, right? It takes the energy a really long time, light a long time to get out of this zone. Then we have a convective zone, which is kind of like a layer of boiling hydrogen, where we kind of go in a circle where hot hydrogen will rise, or radiate away that energy, cool off, and go down again. And it's in a cycle. Understanding these regions of the sun are critical to our understanding of how stars function, but we can't see them, right? We mostly can only see the outer parts of the sun, right? The solar atmosphere. There are three layers of this atmosphere: the photosphere, the chromosphere, and the corona. The photosphere is the lowest of the three layers, and it's what we refer to as the surface of the sun. It's basically the surface that we can see. All the visible light that we see is emitted from this layer, but it also emits light from across the electromagnetic spectrum. So this is a relatively cool layer ranging from about 5,800 Kelvin at the bottom to about 4,800 Kelvin at the top. Absorption features in the solar spectrum, right? So these dark lines on the spectrum on the screen originate in the photosphere because it's cool enough to allow atoms to absorb light at various wavelengths. The photosphere consists of very low density gas, and yet we can't see through it very easily. We can only see about 400 kilometers into the photosphere. It doesn't allow a lot of optical light to get through. And I want to point out something with the spectrum here. Remember the kind of rainbow in the background? This is the continuous kind of black body spectrum of the star. And these dark lines are those absorption features. Next up in the atmosphere is the chromosphere, which is about 1/10,000th as dense as the photosphere. The spectrum of the chromosphere is really dominated by emission lines, which is what happens when atoms drop down an energy level, when they lose energy. Remember, there's actually one emission line in particular that we see a lot, and that is the H alpha emission line at 656.2 nanometers. So this is in the red part of the spectrum. So when we image that, it looks pink. So that is why the chromosphere here looks pink. And we can image the chromosphere of the disk of the sun. If the disk of the sun is blocked by either a filter on a telescope or during a total solar eclipse, like the one we had just what, last year, 2 years ago? Um, so it actually looks kind of like pink fuzz, right, on on the sun. This is an image of from a total solar eclipse. So this image also shows the outermost region of the solar atmosphere called the corona. This region extends several million kilometers from the sun and is about a millionth as bright as the photosphere. Um, this too can only be seen if we somehow block out the disk of the sun, like during a solar eclipse, or we can also use an instrument called a coronagraph, and that covers up the disk of the sun. So the corona is fairly hot, about 2 million Kelvin. Um, and this means that some of that coronal gas will be flung out into space as solar wind. So solar wind is basically just charged particles hurling through space. The sun will emit about 1 million tons of this material into space every second. So the sun is a relatively quiet star, but that doesn't mean that there's not a lot going on and that it's not going through its own cycles and processes. The sun is still really dynamic. And one of those cycles is the solar sunspot cycle. So roughly every 11 years, the sun's magnetic field will flip, meaning that the sun's north and south poles will switch. This switch affects the activity on the surface of the sun, like sunspots, which are caused by the sun's magnetic fields. As the cycle goes on, the number of sunspots we see increases. So the main visual indication of this cycle is just the number of sunspots we see on the surface of the sun. A sunspot is a cooler region on the sun's surface, and they're caused by the kind of twisting and mangling of the sun's magnetic field from within the sun's convective zone. Individual sunspots can last anywhere from a few days to a few months, and the electric field gets all tangled because of this thing called there's differential rotation. The kind of the middle of the star, the sun, as it spins, will move at a different speed than at the poles. So the sun is kind of rotating at different speeds at different spots. So the magnetic field in those locations can get very complicated. Um, Dr. Hassel has some demonstration videos that can illustrate this further. So as you can see from this image at the top, sunspots show up as darker spots on the sun and are often the size of large planets. So this plot at the bottom shows the solar cycle since about the early 1600s through about 2010. And you can see the dips and the peaks of a roughly 11-year cycle. Sunspots are actually the subject of an unsolved astronomy mystery. So from about 1645 to 1715 was an unusually inactive time for the sun called the Maunder minimum. From about 1672 to 1699, they had only about 50 sunspots observed on the sun. So in modern times, we'd see, tens of thousands of sunspots during a similar time frame, and astronomers still don't know why. But this prolonged period of inactivity did still show an 11-year cycle, and we've had much more obvious peaks and valleys ever since. The cycle starts with something called solar minimum. During this time, we don't see very many sunspots. In the middle of the cycle is solar maximum, where we see many, many sunspots. So this is an image comparing the solar minimum of December 2019 with the previous solar maximum of April 2014. You can see basically no sunspots right at solar minimum, and you can see many gigantic sunspots at solar maximum. So the intensity of solar maximum isn't necessarily the same every time it comes around. Some solar maxima are incredibly intense, while others are not. So you can see from this zoomed in solar cycle plot, the 2014 solar maximum was not as intense as years past. The reason for this isn't clear, and predicting the intensity of sunspot activity is really hard. In fact, the red line here is the prediction for the next solar maximum, which is basically predicted to be this year. And the models didn't predict anything very intense. However, scientists are now thinking that actually it may be a fairly intense solar maximum. So probably over the next year or so, we can expect to see increase in sunspot activity on the surface of the sun. But what is very important is you should not take out a telescope or binoculars and look at the sun. That's very dangerous. You're very likely to permanently damage your eyes. You should only use visual aids that use a high quality solar filter. It's the only way you can um, look at the sun directly safely. But these sunspots can be viewed with a telescope with a solar filter, or if you still have eclipse glasses from the eclipse last year, you may be able to use those as well. Sunspots are also associated with more intense aurora, right? Northern and southern lights. So auroras are caused by the sun hurling tons of plasma into space, and those charged particles interacting with Earth's magnetic field. The sun is kind of constantly flinging plasma into space being via solar wind, but the really big plasma flinging event is called a coronal mass ejection, and that's something like this on your screen. Um, and these things are very associated with sunspots. So coronal mass ejections occur when the sun's magnetic field gets so twisted up, they kind of have to realign in some way. This can cause a star like our sun to eject literally tons of plasma, right? Tons of charged particles out into space. This ejection of plasma is a coronal mass ejection, and they happen a lot where the sun's magnetic field lines get all twisted up, like around sunspot groups or sunspot pairs. So when we enter the solar maximum phase of the solar cycle, there is an increased chance of very intense auroras. And this means that the northern lights could be brighter and be seen further south than normal. Forecasting aurora is difficult, and we can only really do it reliably, maybe like an hour in advance. The Space Weather Prediction Center at the National Oceanic and Atmospheric Administration has a handy little dashboard where you can follow aurora predictions, though. They include a handy chart of the planetary K index. This index tells us the intensity of geomagnetic storms, right? These events that hurl plasma towards the Earth and are associated with auroras. The lower the planetary K index, the milder the geomagnetic storms and the milder the aurora. To have the possibility to see auroras here in upstate New York and really kind of the rest of the northern US, we need a K index of 8 or 9, which is really kind of the very top of the scale. So this is a plot of the K index for a couple of days, and you can see it hasn't, it didn't really get above 3. And that's way too low to be seen in upstate New York. But here's an example of how the K index affects where auroras show up. So green shows kind of low probability of aurora, and red is high probability. The K index of 3 produces a pretty weak aurora. So over here, to see northern lights here in upstate New York, we really need a solar storm of like an 8 or a 9. So the storm we need to get this type of atmospheric event is pretty large, but given that we're at least moving into solar maximum, I think it's kind of worth keeping track of. There are other flashy behaviors that correspond with sunspots. So solar flares occur in complex sunspot groups and hurl vast quantities of particles and radiation into space. They can be extremely energetic. The most energetic can be like 100 trillion nuclear bombs going off at once. So a lot of energy. Uh, Similar but different is a solar prominence, which are these kind of gigantic loops of plasma that occur near sunspots that can last for weeks. They're anchored at both ends in the photosphere, and sometimes they can quote unquote break and fling plasma and particles into space. The last thing I want to talk about are neutrinos. We saw that during the PP chain, neutrinos are produced, but what are they? So a neutrino is a high energy subatomic particle. They are teeny tiny. They're about 8 orders of magnitude less massive than a single electron, and they have no charge. So they are totally electrically neutral particles. Okay, so neutrinos are small, electrically neutral, but not rare. About 100 trillion neutrinos pass through your body every second. Don't be alarmed, they're not dangerous. Um, they are streaming around all the time and we don't notice. So you might think that neutrinos would be very easy to detect, but in fact, they aren't. Neutrinos don't interact much with anything at all. They fly through space as though it were perfectly empty, right? Nothing to get in the neutrino's way. They interact, though, every once in a while with atoms and molecules. But compared with how many there are flying around, the number of interactions is really kind of vanishingly small. They're often called a ghost particle. Neutrinos, remember, are formed, well, they're formed through a variety of processes that usually involve some kind of radioactive decay, where an unstable atomic nucleus loses energy. And remember, that's exactly what happens in the PP chain. Here's another example of it. At the beginning, when we had our two hydrogen nuclei fuse together or collide together, it produced a neutrino. These little particles have been interesting astrophysically for a while, and they're actually the center of what was a real pickle in astronomy called the solar neutrino problem. Because remember, the sun produces a lot of neutrinos. They're this natural byproduct of the PP chain, the proton-proton chain. Um, which, remember at the very beginning of this very long lecture, is that nuclear reaction in the sun that causes hydrogen to fuse into helium. Um, it's been known for a while that neutrinos come in three quote-unquote flavors. There's the electron neutrino, the muon neutrino, and the tau neutrino. The proton-proton chain produces mostly electron neutrinos. So that's what we expected to find when we looked in the 1960s. We expected to find heaps and heaps of electron neutrinos, but we didn't. The plot on your screen here shows the discrepancy between what was theoretically predicted, sorry, in yellow, red, green, and black bars, and the actual measurements of electron neutrinos in blue. Researchers found about a third as many neutrinos as they thought they should. So this is highly perplexing. Could this mean that how we think the sun works is wrong, right? So it turns out that what we knew about the sun was right, but what we thought we knew about neutrinos was wrong. So remember, neutrinos, they're much, much less massive than electrons, right? Fractions of an electron. Through the 1970s, physicists didn't think neutrinos had any mass at all. They thought they were actually massless particles. But in 1987, astronomers detected neutrinos from a supernova explosion in one of these nearby galaxies called the Large Magellanic Cloud, and determined that neutrinos actually do have mass. If neutrinos have mass, this means that through some quantum mechanical weirdness, it's actually possible for neutrinos to change their flavor. Electron neutrinos can become muon or tau neutrinos. Muon neutrinos can become electron or tau neutrinos, and tau neutrinos can become electron or muon neutrinos. So think about how strange this is, right? Like my cat doesn't randomly turn into someone else's cat, right? Um, Words on a page don't randomly reorganize themselves into other words, but a neutrino can and does change its flavor. We observed this for the first time in 1998. It is called neutrino oscillation, and it won a 2015 Nobel Prize in Physics. And it explains why we were only detecting a third of the neutrinos we were expecting to from the sun. Our detector was only designed to detect electron neutrinos. So even though electron neutrinos may be what is created in the sun, during their journey from the sun to the earth, two-thirds of them will be a different flavor when they arrive. I think that's pretty wild. Okay, so that is it for this lecture. I know it was a long lecture this week, but thank you for sticking with me. Remember to read the chapters in your book, and if you have any questions, just shoot me an email or come by my office hours.